I'm going to go through a notebook written in Python, and for which there is an introduction that I'm just going to skip because you probably already have listened to me talking about noise and image denoising. So in this notebook, I'm going to tackle just noise and denoising. And in order to do that, I'm going to load those regular packages that we often use and talk about noise distributions and artificial noise generation. So we are going to study three types of noise. Uniform, that means all range of values that may be added to the image are equally probable. The Gaussian or normal distributed noise, in which the values to be added to the image follow a normal distribution with some mean and standard deviation. And also, we are going to study a nonlinear noise process that is the impulsive noise, also known as the salt and pepper. And but correcting myself, the impulsive noise allows us to observe only pepper noise, which is associated with value 0, and the salt noise, which is associated with the value 255. There are also other values that can be considered. Some impulsive noise also generate values that are not 0 or 255. Okay. Let us start with the uniform noise. So this function here, you may inspect by yourself. It's basically generating a matrix with uniform noise to be added to an image. So what I'm going to do is to define the size of the noise matrix and the probability for the uniform noise generation. This has a 10% probability. I can increase it or decrease it. And also, I'm going to return the matrix with uniform noise to be added to the image. In order to do that, I'm going to multiply the probability with the maximum value. And then in this case, I'm taking, for example, just in the case of 0.1, the value here will be 10%, so 25.5. And I'm going to divide it by 2. Why is that? Because I want to sum noise, sum values, but I also want to subtract values. So the noise is an additive process in this case, but that means I should be able to add a negative or a positive value. And finally, it is centered at a value with probability 0.1, and then I'm converting it to integer. And the matrix is basically a random integer value in between minus the number of levels here and plus levels with the size defined. I'm going to load this image that has only 3 gray levels: 32, 127, and 186. And I'm going to create the uniform noise. So in here, this variable here gets the matrix of uniform noise with probability 15%. I'm going to take the image, the input image, as type integer to avoid problems of overflow, add the noise, and then I'm going to clip all values that are below 0 to 0 and above 255 to 255. So this np.clip function is useful to clip values that are beyond some threshold that I define here. And then I'm going to show the histograms of both images. So let us see here. Let me try to redefine here in the hope that it became larger a little bit. So yeah, in this case I have the noise-free image. The histogram you can see here, so just 3 values. And then when I add uniform noise, the histogram changes, and then it became the three values here become a variety of values. If I just print the unique values of the image with uniform noise, now there are much more values that are available at this matrix. Okay, note how the original image, which is noise free, has just those three intensity values. I just changed them, so let me do that. 32, 127, and 186. When we add uniform noise, values are added or subtracted, producing a wider range of intensities around the original values. Note how the values are approximately uniform. Now I'm going to do the same or similar approach, but generating a Gaussian noise matrix with some size, and now I have mean and standard deviation as parameters. In order to do that, I'm going to just create a normal series of random variables, random values with this mean and standard deviation, and then with the same size of the matrix. And then I'm going to multiply it with 255 because the maximum is 1. It goes to 255, and then this way I have a matrix to be added to the original image. I'm going to then first, so here I'm creating, similarly to the example above, so creating the noise matrix to be added, then adding and clipping values below 0 or above 255, taking the histogram, and let's see. So this is the histogram, so we can note the difference between this histogram and the other one. In this case we have a Gaussian shape for the intensity values. Because of the resolution here, it has those gaps here, but they probably don't exist. This is because I just used a regular value here. Let me change it. Yeah, this is more like what we wanted to observe. Anyway, the values here are more likely to are more frequent around the intensity values, and then fall exponentially to plus and minus this value. Note also, because of this tail of the distribution was not completed, all values that were supposed to have, it doesn't help zooming it out, so all values here that are below 0 become 0, so that's why I have a peak here at 0. And this is the image. And finally, the impulsive noise. So the impulsive noise, in here I made it by using a for loop. There are better ways to do that, but I wanted to be sure that the way I implemented was correct. So I could instead use a matrix as I was using before, but here I'm going to take the image as input instead of producing a matrix to be added. In this case, the impulsive noise is not an additive noise. It is nonlinear and correlated with uncorrelated with the pixels, and it doesn't happen. It doesn't occur uniformly or in the same way all along the image. So this is why I just did this double for loop, right? But in practice, try not to use that. So I'm basically going through X and Y and then creating a random number So this mimics this effect. And if the random variable is below some probability, then I'm taking another random number. If it's above 0.5, it becomes salt or white, and below or equal to 0.5, then it becomes a black pixel, 0, or pepper noise. Just created the histogram and let us plot it. You can see that the image is very corrupted, but what we have is we don't change the original intensities, we just add 0 and 255. If I add a stronger noise, then the image will become more and more corrupt, and we will observe a larger frequency of those two values. Let us just go back to a smaller value. This is similar also for those other values. Let's say that I want to increase the standard deviation here by a large margin. So this makes the histogram very weird because many values were clipped to 0 and 255. So it's even difficult to see the 3 Gaussians here. Yeah, that's more like 3 Gaussians. And as I decrease, it becomes more like we are used to perceive. We can even decrease it and see the peaks that has a much more narrow distribution here. Okay. The same happens with the uniform noise. If I increase it, it starts to even merge, so those values start merging with the others here. And if I decrease, then the distribution is much narrow here. Becomes narrow. Let us just go back to 0.1 and stay with this. Then the denoising methods, considering that we have an additive noise formation, we could just generate noise and subtract from the image, right? So if the degradation process is an addition, in principle we could just remove it by subtracting it. But assuming we don't have the original matrix that was used to add, I could, for example, generate noise and subtract it from the image. But in order to see if this is right, let us compute the RMSE, or the root mean square error. So, and compare them. So the error between the noisy and the original image is around 7%, while so 7% of the values are corrupted. And the error between the restored version, so the image that I use, that I subtracted the noise, and the original is much higher. So instead of decreasing the error, I ended up increasing it. So we can confirm here that in fact we even added more noise. So this image on the right hand side visually appears to have more noise than the other. So what can we do? We can use denoising filters. In order to do that, I'm going to use an FFT version of a filter. So I'm filtering on the Fourier domain. You can check it out on at the notebook with detail what I'm doing. So in here I'm reading a new image and including Gaussian noise, and then creating a 5x5 mean filter, and we are going to use the FFT to filter it. This last line here is the line that produces the filtering. So I'm taking G as the noisy image and then filter it with using this mean filter here. So as we expected, the mean filter caused the image to be blur, to become blur. So it removes the noise or diminishes the noise, but also causes this effect of also smoothing out the borders and the details of the image. When a filter is linear, we can compute it with FFTs, but for order statistics filters, such as median, it's harder to optimize. In here, I'm doing it pixel-wise, but there are other implementations or more efficient implementations in the packages. You can use them, but I implemented from scratch here for you to understand how it works. We could also change the filter. I just use a regular 5x5 mean filter, but you can use an adaptive filter, a weighted version of it. It's up to you now to explore in that sense. Let's see how the median filter behaves. You note that it takes a little bit longer, and let us compare them. So the mean filter and the median filter. We probably had to zoom them to better perceive the differences. Let's see if that works. Yeah, a little bit more, so 80 pixels, around 80 pixels, so it's square in here. Let me take from 80, so 100 pixels. Okay, let's just repeat that with the mean and median. Okay, so as you may see here, the median filter is more adequate to preserve borders, although it is not completely adequate, because it also creates unrealistic borders, so it creates false borders. Let us do the same now, but for an image with salt and pepper noise. Compare a mean filter and a median filter with size 3x3. Okay. So the noise here, it's noisy free. Noise free. This is the noisy image with salt and pepper. I included a large amount, so 20% of the pixels are corrupted. And then this is the noisy version. With the mean filter, it ends up smoothing out even the outliers. So this image is not acceptable. But with the median filter, it is much better. If there is a decrease here in the probability, the results are really impressive for the median filter. We lost this first line here, that's very small, but the remaining ones are really good. So, and if I decrease it, it's almost perfect in this case. I'm probably not going to be able to reconstruct this very thin line here, because it has only 1 pixel in size, so in width. Because of that, I cannot restore it, because any filter will just like merge those two regions together. So this example shows you how relevant it is to know the noise process before designing a filter to remove it. So I invite you to explore different filters, so build your own filters and try with those images and different noise types.